this video, we'll be talking about rational functions part B, the more complex rational functions. A rational function is any function of the form f of x equals g of x over h of x, where g and h are both polynomials. So now we're going to have more than just 2 over x. We're going to have an expression on the top and an expression on the bottom, both of which can have x in them. Luckily for this course at this point, we only need to worry about functions in which g and h are both linear. So as you can see on this example, the one at the top is 2 linear functions, one on top and one on bottom. The second example is a polynomial on the top that's x to the 3rd power. The denominator is x squared. We're not going to deal with functions like that just yet in this course. So today we're just dealing with ones where it's a linear function on top and on bottom. A little bit simpler, but they still do both have x on top and bottom. So the rules are going to be a bit different. So this is the general form for the ones we'll be dealing with today. Ax plus b is just a general linear function like mx plus b, right, where there's something multiplied by x and then there's something added or subtracted. Same thing on the denominator, but we use c and d. A, b, c, and d are all just going to be numbers here, but it's linear on top and linear on bottom. Finding the domain and the range, as well as the vertical and horizontal asymptotes, is going to be slightly different from what we've seen before. So in the last lesson, we saw rational functions that had h and k. And h and k made it really clear where the asymptotes are moving to, because the parent function had asymptotes at x equals 0 and y equals 0, and then h and k would shift the asymptotes left and right and up and down to their new locations. In the ones we're dealing with today, we have x on the top and the bottom. We can't see h and k, so we're not going to be able to use h and k to figure out where the asymptotes are or where this function exists. So let's learn the rules for these types of functions. You already know how to find intercepts, so if asked how to find the x-intercept, we're going to change y to 0. And if asked how to find a y-intercept, you're going to change x to 0, and then solve the resulting equation in each case. So this is the same across all functions that we learn. Vertical asymptotes for this function are going to be located at the solutions to the denominator equals 0. It used to just be that the vertical asymptote would be at 0, but now the denominator is going to have a more complex expression in it. So we're going to do set the denominator equal to 0 and solve for that. That gives us the vertical asymptote because the denominator of a fraction is not allowed to equal 0, so whatever value for x you get is that value for x where the function can't exist because it makes the denominator be 0. So that's why we draw an asymptote there. Horizontal asymptote's a little funny for these functions. It's going to be y equals, because it's a horizontal line, a over c, which is basically the leading coefficient over the leading coefficient, a over c. And then the domain is going to be all real numbers except for the location of the vertical asymptote, and the range is going to be all real numbers for y except for the location of the horizontal asymptote, and those you would have just found. All right, so in this example, we're going to play with some numbers. We're going to find the domain and range, sketch the graph, indicate asymptotes and intercepts. So we're finding everything here. I'm not going to start with the graph or even with the domain and range. I'm going to start with the asymptotes. They're the most important things to find about this function. So the vertical asymptote is going to be located at the denominator set equal to 0 and then solved. So here x equals -5. Horizontal asymptote is going to be located at y equals coefficient over coefficient, which here is 2 over 1, which is just y equals 2. The domain, therefore, is going to be x such that x is an element of all real numbers except for the location of that vertical asymptote you just found. So x can't equal -5. That's why there's a dotted line barrier on the function there. And the range is all real numbers such that y cannot equal 2. That's why there's a barrier there, because y is never going to be 2 for this function. Before graphing it, I'm also going to get the intercepts, and then I'll have plenty of information to put this thing on the graph. I'll do the y-intercept first because that tends to be easier. I'm going to change x to 0. So y equals, still y, 2 times 0 minus 6 over 0 plus 5. These are both 0, so y equals -6 over 5. That means the function has a point at 0, -6 over 5. For an x-intercept, I change y to 0. So 0 equals 2x minus 6 over x plus 5. The algebra involved here involves multiplying both sides by this x plus 5 to get rid of this denominator. But luckily, x plus 5, when you multiply it by 0, just becomes 0. And on this side, the x plus 5 cancels out. And so you end up just having to solve the numerator equal to 0. And so 0 equals, or 6 equals 2x, and 3 equals x. That means this function has a point at 3, comma, 0. And now I have enough information to get a sketch of this thing accurate. So I'm going to go ahead and create the coordinate plane. First thing I want to do is plot the asymptotes, sketch those asymptotes. I have a vertical one at x equals negative 5. 1, 2, 3, 4, 5. And I have a horizontal one at y equals 2. Now I have the guidelines for where my function's going to be. I can plot any intercepts that I have. I have one at 3, 0, and one at negative 6/5, which is just a little past negative 1. So that gives me an idea for this branch. And then since this is just a sketch, I'm going to create a similar curve in the upper left-hand corner that's nice and symmetric across these asymptotes. And that's good enough for a sketch. It did say to label, clearly indicate. So I do want to label 3, 0 on the graph. I want to label 0, negative 6/5 on the graph. I want to label my asymptotes, y equals 2, and this asymptote at x equals negative 5. And that way it's really clear to your grader where the location of everything is, even if your graph is just a sketch. To create a more accurate graph, bring this out here. To create a more accurate graph, we can follow these steps. Find and sketch the asymptotes first. That's got to be your first step. Plot any intercepts that you found and label those as well, but sometimes that's not good enough to get a full picture. So the next thing you're going to want to do, the new bit, is step 2. Create a table of values with some things to the left and some things to the right. Basically mean use the function, plug some stuff in. Figure out where is this function on the left, where is this function on the right of the vertical asymptote, which is the new center for your graph. You don't need many points. Try maybe 2 whole numbers on either side. And then you'll have enough dots to create an accurate picture. So you'll just connect the dots. So let's do one like that, where we're creating a more accurate picture. Here's the function. We still cannot start with the graph. We start with the asymptotes. So vertical asymptote is located at wherever the denominator equals 0. So here it's x equals 2. Horizontal asymptote is located at coefficient over coefficient, which here is a half. So I'm going to sketch those asymptotes on the graph. And now I can see where the new center for the graph should be. Graph is centered here at x equals 2. And so when I plug in a few things to the left and to the right, I'll figure out where these branches need to be. So that immediately to the right of this asymptote is 3, 4, 5, a few numbers on this side. And immediately to the left we have 1, 0, negative 1. You're going to want 2 points, maybe 3 points to either side to really get a good picture of this curve. So maybe I'll plug in, and you can use your calculator if you have one to get these points. You're basically just evaluating f of negative 1, f of 0, and f of 1. And then you want to evaluate f of 3, f of 4, and f of 5. Sorry for the pen being a little funny here. And by evaluating each of these, you'll get an output that shows you where the function should be. So like when I plug in 3, I get 3 plus 1 on top, which is 4. 6 minus 4 on bottom, which is 2. And so now I know I have a point at 3, comma 2 on this function. When I plug in 4, I get 5 over, let's say, 8 minus 4, which is 4. So 5/4. So now I know I have a point at 4, comma 5/4, which is a little bit over 1. And you can plug in 5 and get the rest of this trend as well. And now you have a more accurate picture for where these branches need to be. You can plug in negative 1, and this is where you figure out that that's actually one of the intercepts, and negative 1, 0 is right on this graph. You can plug in 0 and figure out that we've got negative 1/4. And again, you can plug in more points to get a more accurate picture. So by plugging in points, you get an accurate picture of where the branches need to be. But remember that for a sketch, it's okay to just use the intercepts and try to create a nice symmetrical hyperbola. State the domain and range. By now you should know. Domain is going to be all real numbers except for the location of the vertical asymptote. So here x cannot equal 2. And range is going to be all real numbers except for the location of the horizontal asymptote, which here is 1/2. Make sure that says cannot equals. And that is all.